So what'd you get for this limit? It's 8/3 again. That's an amazing fact. All of this actually is pretty amazing. So because we know that the left-hand sum underestimates the increasing function, right? Here's the right-hand sum. All the rectangles stick over. That's an overestimate. The true area has to be less than that. Here's the left-hand sum. All the rectangles are under. They have to underestimate. The area has to be more than that. And yet those numbers are both the same. That's the amazing thing. So what is going on? The true area has to be, so we've been naively saying the true area has to be greater than 8/3 because the left-hand sum underestimates the increasing function. That's true for a finite sum, but this is not a finite sum, it's infinite. So it could be equal. We haven't proved that it's equal yet, but it could be. So here's what goes on. The right-hand sum is, well, all right. So yeah, that's that. So let's look at what is the difference between these two, right? My right-hand sum, let me just write this, that the limit as n approaches infinity of the right-hand sum is 8/3, and the limit as n approaches infinity of the left-hand sum is also 8/3. Like, how can that be with the way they're laid out? So another thing that you can look at is, what is the difference between the right-hand sum and the left-hand sum? I mean, they're really similar, right? So what is the difference between the two? The difference between the left-hand sum and the right-hand sum is, well, what's the difference between the two? It's between positive 12n and negative 12n over 3n squared. The difference between them is 24n over 3n squared. Right? Also known as 8/n. So what's the limit as n approaches infinity of 8/n? What's the limit as n approaches infinity of 8/n? Why, it's 0, because the largest exponent is the denominator. So what this is saying is, as the number of rectangles approaches infinity, the difference between the left-hand and the right-hand sum disappears. It's gone. What's going on? The delta x, the width of the rectangles, is b minus a over n, in this case 2/n, but b minus a are constants, doesn't matter what they are. The limit is as n approaches infinity of b minus a over n is 0, as long as b is not equal to a. All right, so that means the width of the rectangles is going to 0. So you can think, like, as the width of these rectangles gets smaller and smaller, right, the delta x is going towards 0. What's happening is that whether I evaluated the left or the right doesn't matter, because the left and right are becoming the same point. And that's going to be critical for us to get a way to find these sums that is more manageable and less unwieldy. Like, this was a lot of work to do, but I like to do this. I do it with my students every year to show, you know, what you're really doing. You can really do this limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. That's a limit that we can evaluate like any other limit and get a number. And then what happens, if we look on our last page, is that since the area from the left is less than or equal to a is less than or equal to the area to the right, and the limit as n approaches infinity of a from the left is equal to the limit as n approaches infinity of a from the right, which is equal to 8/3, it follows that the a has to be 8/3. You know, this conclusion right here makes me hungry. Is it lunchtime? Is it lunchtime? Because I want a sandwich. I want the sandwich theorem. Look at this. Look at this. Remember page 65? You remember way back at the beginning of the school year, and we talked about the sandwich theorem? F of x is in between g of x and h of x, and the limit of the two outside functions is the same. That means the limit of the function in between them has to also be the same. A picture, if the two limits are the same, then something that's trapped in between them is the same. But for us, our trapped in between function is constant. All right? So one way to look at what's going on is that I have the left-hand sum is less than or equal to a, is less than or equal to the right-hand sum. And as n approaches infinity, the left-hand sum approaches 8/3, and the right-hand sum approaches 8/3. That means the a has to also approach 8/3. But a is a constant. It doesn't approach things. It just is a constant. So if a is approaching 8/3, that means it was always 8/3. So this limit gives us an exact value. Many things are very surprising here. Among them, one of the surprising things to me is that you have the curve x squared. You're evaluating it from 0 to 2. That area is exactly a rational number. It is exactly 2 2/3. That's the exact true area of both of those pictures, because that's the true area if you don't do any rectangles at all. The true area is 2 2/3. All right, so let's actually fill out the bottom part, because the bottom part is the real conclusion here. Okay, so what do I want you to write here? And remember, I want you to turn in your version of this where you write out everything that we've written. You don't have to write out every single thing, like you don't have to write out this. Just write your fully explained answers to each question, because I want you to show that you've taken good notes on this and that you've worked through it. And that's going to be your only homework that's assigned for this. I can't assign you a homework on this. I don't expect you to do this on your own. But just your homework is to show me that you did this with me today. So what is the Riemann sum? It is the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. All right, that's the Riemann sum definition of an integral. Many people will correctly say that only this is a true Riemann sum, and the finite ones are not really Riemann sums. Okay, but we don't really have any other name for them, so I call them Riemann sums anyway. But with the limit as n approaches infinity makes a true Riemann sum. All right, this word is what we've been working for this entire time. The integral, the integral, the definite integral. The integral from a to b of f of x dx. That's what this means. All right. In our particular example, it's the integral from 0 to 2 of x squared dx, which we came to know is equal to 8/3. And this is what we want next, is a way to calculate this. And by the way, just like when we first learned derivatives, we went through a lot of work to find out that this integral is 8/3. But after a couple of weeks, so in mid-January, you're going to be able to look at this and get 8/3 in less than half of 1 minute. Less than half of 1 minute to get from here to here. All right. But as usual, we need the theoretical framework that goes on in the background. Otherwise, you're just writing numbers. You don't know where they come from. You need to know what's going on behind them. What is the geometric interpretation of this? It is the area under the curve f of x from A to B. All right, it's the area under the curve. That's the geometric interpretation. Now we'll talk more about this. The geometric interpretation is actually more complicated than that. So for example, if you have a function that goes below the x-axis, we're going to consider the area under the curve, this part of the area. First of all, we're going to call it the area under the curve, even though it's over the curve, and then we're going to call it negative. Right? So we're going to say this is the positive area under the curve, this is the negative area under the curve. So this area under the curve is an idea that we're going to develop further. All right, but this is where we got to. Now, a couple of words about the notation. You know, if you think about where the notation dy dx came from, okay, the limit as delta x approaches 0 of delta y over delta x, that's what dy dx means. All right, this notation comes the same direction. The limit as n approaches infinity, and remember what we said here, as n approaches infinity, delta x approaches 0. So this is also a limit as delta x approaches 0. So the delta x becomes a dx, just like this delta x became a dx. This sign that we use that I draw so terribly, and it's really supposed to be a nice thing like that, it is a Greek capital sigma. It is the letter S. This integral was designed to be a stretchy S to represent an infinite sum. That's what that symbol is supposed to represent. So the sum becomes an integral, the delta x becomes a dx, the f of x sub I becomes f of x, and the limit as n approaches infinity is just represented by that whole thing. That is called a definite integral. The integral from a to b of f of x dx is how you say that. The integral from, because you know, it's English is littered with prepositions, and you got to get all the prepositions right. The integral from a to b of f of x dx. I mean, it's f of x. So how many prepositions? 1, 2, 3, 4 prepositions in one. It's not even a sentence. It's a phrase. 4 prepositions. Welcome to the English language. It's because it's not inflected, if you want to look that up. So the integral from a to b of f of x dx, that's how you say that, the integral from a to b of f of x dx. All right, so the rest of our time between now and like April is going to be tied up in how do we easily get these integrals and what can we do with them. Finding the area under the curve is just a tiny fraction of what you can do with this thing, and that's what we're going to explore next.